MS Ramaiah University of Applied Sciences.
Water jets are commonly used in day-to-day life. Take the example of a house tap that releases water jet when open, or a garden hose that is used to irrigate plants at home. A network of sprinklers are generally used for irrigation in a large-scale cultivation. A sprinkler is a nozzle device that converts fluid pressure into jet velocity. A water jet is also used for entertainment. An excellent example is the musical fountain at Brindavan Gardens at KRS Dam. When the jet of water comes in contact with the surface, it is termed as the impact of jet. A high impact water jet can actually cut through metals. Water jet cutting is also used in manufacturing. Water jets are used in this process at high velocities to cut metals as thick as 2 inches. Hydraulic turbines are devices that convert kinetic energy of a fluid to mechanical work. The shape of a hydraulic turbine blade is optimized for efficient utilization of the fluid energy from the water jet. The study of the impact of jets on vanes is necessary to understand the energy transfer from the water jet to the vane.
Why do we need to concentrate on the impact of jets? Let us look at the learning outcomes. At the end of the experiment, the student will be able to demonstrate the amount of energy transfer of a jet on a surface. The student will also be able to explain the mechanism of formation of jets. But then, how is it done? We shall actually conduct the experiment on impact of jets. The losses involved during the impact is analyzed. The theoretical force of the impact with the measured value is compared. Before that, how are jets actually formed? It follows the Bernoulli's principle. The principle states that at any arbitrary point in a fluid flow, the algebraic sum of pressure head, kinetic head, and potential head remains a constant, that is, P by rho g plus V square by 2g plus z equal to a constant. For the equation, we assume that the flow is steady, inviscid, frictionless, and incompressible. Hence, at a same potential head, a drop in pressure leads to an increase in kinetic head, or in other words, forms a fluid jet of high velocity. Let us apply the Bernoulli's principle to a nozzle. A nozzle is a device that works on the Bernoulli's principle to convert pressure head of a fluid into kinetic head. The design of the nozzle consists of a change in diameter that creates a pressure drop. Hence, high velocity jets are formed at the expense of pressure drop. We know from Newton's second law of motion that the force applied on an object is directly proportional to the acceleration of the object produced by the force. Also, this acceleration is inversely proportional to the mass of the object. If F is the force and m the mass and a be the acceleration of the object, we know that F equal to m times a. From the figure, if the velocity of the jet is impacting a surface normal to the direction of the jet, then F equal to m times a, that is m times change in velocity by time. In other words, we can write it as mass flow rate times change in velocity. Here, the change in velocity is the difference between the initial velocity and the final velocity. But the final velocity will be taken to be 0. By solving the equation, we get F equal to rho times a times square of velocity. This is the force of impact. For a plate inclined at an angle theta, then we will have resolution of forces. There will be 3 forces, one normal to it, one in the x direction, and one in the y direction. The expression for normal force is rho times a times square of the velocity, multiplied by the sine of the angle, and the force in the x direction is rho times a times square of the velocity into square of the sine of the angle, and the force in the y direction is rho times a times square of the velocity multiplied by the cos of the angle and the sine of the angle made by the plate to the axis of the jet. For a curved plate or a vane, the force can be reduced to 2 times rho times a into square of the velocity. Here, the angle during the course of this impact, there are losses associated with the jet that leads to reduced amount of the force of impact. The flow of the fluid is not completely steady. There exists friction between the surface of the plate and the fluid, which reduces the impact. The energy with which the fluid comes in contact with the vane is not completely converted to the force of impact. Hence, the actual force of impact is lower than the theoretical force derived. In order to estimate or evaluate the actual force of the jet impacting on a surface, we may use a coefficient defined as the coefficient of impact as Ci, which is the ratio of actual force to the theoretical force. We must know that the coefficient of impact is always less than 1. At MSRUS laboratory, we have a setup to calculate the coefficient of impact of jets. This is the experimental setup that we are having at our fluid mechanics laboratory. The experimental setup consists of a storage tank for water storage. It is connected to a centrifugal pump to pump the water. A discharge valve at the downstream of the pump is used to control the flow rate of water. Further, it is connected to a flow meter. Here, we use a rotameter to indicate the volumetric flow rate of the water. A nozzle has been fitted on the piping to generate water jets. 3 nozzles of varying diameters, 4 mm, 6 mm, and 8 mm can be fitted on the piping to vary the diameters of the jet. It consists of a stationary vane receiving the impact of water jets. Further, it is connected to a load cell from the stationary vane that can directly give an indication on a digital scale of the actual force of impact due to the water jets on vanes. This is the experimental setup to calculate the impact of jet on vanes. Now if you see inside, we have a nozzle from which a fluid of high velocity comes and impacts stationary vane. This stationary vane is connected to a load cell shaft, which in turn is connected to a load cell which will give the value of the force of impact, and this value can be read on the digital scale over here. In order to create the high velocity of the fluid, what we have here is a sump tank to store the water. This is the pump which will take the suction from the sump tank, and then from the discharge we have a discharge valve which is connected to a flow meter. Through the flow meter we can control the flow rate of the fluid that is flowing through the pipeline, which is finally coming towards the nozzle. And because of the nozzle construction, we get a very high velocity of the fluid. So this high velocity fluid comes and impacts on the stationary vane with some force of impact. So that force of impact can be sensed by the load cell, and that force will be actually showed in the load cell value. Here I have fixed a 4 mm nozzle and a hemispherical vane. In our setup, we are having 3 types of vanes. One is a hemispherical vane, and another 2 are inclined flat plate and perpendicular flat plate vanes. So for now I have fixed a hemispherical vane,
And in the nozzles, we are having three types of nozzle diameters. Right now, I have fixed 4 mm nozzle. Also, we are having a 6 mm and an 8 mm nozzle. This is a 4 mm nozzle, this is a 6 mm nozzle, and this an 8 mm nozzle. The difference in the diameters will have different jet velocities. The lowest diameter will have higher jet velocities when compared to the higher diameter nozzle. Now, before conducting the experiment, we have to calibrate the load cell. We need to make sure that this value is showing 0, 0. If not, then we'll have to calibrate it. Right now, as it is showing 0, 0, let us go ahead and start the experiment. I will be starting the pump and then controlling the discharge valve to a flow rate of 15 liters per minute. I have set the flow rate at 15 liters per minute and the fluid is exerting a force on the vane. This scale is showing a value of 0.33 kgs. So this is the force of impact of the fluid that is being exerted on the hemispherical vane.
Let us calculate the coefficient of impact. The observations made from the experiment is tabulated as flow rate for a flow rate of 15 lpm, the nozzle diameter being 4 mm, the load cell returned a value of 0.33 kg. Converting the flow rate into SI units, we get 2.5 into 10 to the power minus 4 meter cube per second. The velocity of the fluid at the nozzle exit is calculated as V equals flow rate by the cross-sectional area of the nozzle, and the velocity is found out to be 19.89 meters per second. The theoretical force of impact for a curved vane with theta equal to 0 is 2 times rho times area into the square of the velocity. Further, by calculating, we arrive at a theoretical force of 9.93 newtons. The actual force of impact, which was in kgs, is converted into newtons, which is 3.23 newtons. Hence, the coefficient of impact is found to be 0.326. The same experiment is repeated for varying flow rates and for different vane geometries. The different vane geometries used are a flat vane, an inclined vane at angle of 60 degrees, and the hemispherical vane. The calculations for the coefficient of impact has been made and tabulated in the table. A graph of coefficient of impact against different vane geometries is plotted. We find that for a flat vane, the coefficient of impact is much higher when compared to a hemispherical vane. Let us calculate the theoretical force. The theoretical force may be expressed as mass flow rate times the velocity, or the volumetric flow rate times the density multiplied by the velocity. For a flow rate of 15 liters per minute, the theoretical force obtained is calculated as 4.96 newtons. A graph of theoretical force against the actual force of impact is also plotted. Ideally, it should have written a straight line with equal units on both the axes. A CFD simulation of the setup was made in ANSYS Fluent and solved. The velocity pathline plot show the velocity of the fluid impacting the vane. The initial velocity is found to be around 20 meters per second, and we can observe the fluid being diverted out of the vane. This indicates that not all of the energy is converted into the force of impact. Look at the inference of the experiment. Coefficient of impact is affected by parameters such as fluid velocity, viscosity, and the vane geometry. Flat veins have a higher coefficient of impact compared to hemispherical veins because the exiting fluid is perpendicular to axis of jet for a flat plane. From the simulation, we observe the velocity of the exiting fluid is lower at the surface of the vein due to the friction between the vein surface and the fluid, which could again add to the loss of the force of the impact. Would be the further learning. Let us address some of the following questions. What happens to a high viscosity fluid jet impacting on a veins? Now, considering different vein geometries, what is the behavior of impact of force? If the vein was not stationary, what would be the result of the impact?
At MSR UAS, we spark your imagination unlike any other.